Hi everyone, welcome back. In this particular presentation, we are going to go over some synthesis that involves the electrophilic aromatic substitution reactions. So to get started, what we're going to do is we're going to review some of the synthesis of monosubstituted aromatic compounds that we have already encountered. So here we have a couple of examples where we are starting with benzene and we are trying to make a variety of other aromatic compounds. Again, benzene derivatives here. So the first example is benzene going to chlorobenzene or bromobenzene. And as we know, such a synthesis can be accomplished using chlorine with aluminum trichloride as a catalyst if we are trying to make chlorobenzene, or we could use Br2 with FeBr3 as a catalyst if we want to make the bromobenzene. Similarly, the nitration of benzene, or any aromatic compound for that matter, is achieved using a mixture of nitric acid and sulfuric acid. The sulfonation of benzene is achieved using fuming sulfuric acid, and the active component here, the electrophile, is sulfur trioxide. The alkylation of benzene can be achieved using the Friedel-Crafts alkylation reaction, where we use an alkyl chloride along with aluminum trichloride as a catalyst. So this is the Friedel-Crafts alkylation reaction. Similarly, the acylation of benzene can be achieved by using an acid chloride in presence of aluminum trichloride as a catalyst. So this is the Friedel-Crafts acylation reaction. So these are some of the elementary reactions that we have learned for converting one aromatic into another aromatic, or converting benzene specifically into one of its derivatives. Now, some of these derivatives can be further converted into other compounds. Now, some of these aromatic derivatives that we've made can be converted into other aromatic compounds by subsequent reactions. So for example, the nitro derivative can be reduced using zinc or iron in acidic conditions to give us the amino compound. So the nitro derivative here is converted into an amine. And this reaction, because this is done under acidic conditions, would usually be followed up by a basic workup. Similarly, alkyl benzenes, and specifically the alkyl benzenes which have at least one benzylic hydrogen. So we need at least one benzylic hydrogen. Now this compound here has two benzylic hydrogens, but as long as you have at least one benzylic hydrogen, these alkyl benzenes can be oxidized using a strong oxidizing agent like sodium dichromate, for example, to give benzoic acid. So irrespective of what the starting alkyl benzene is, it is converted into benzoic acid. Similarly, ketones which are derived from the Friedel-Crafts acylation reaction, these can be reduced using zinc amalgam and HCl, so under acidic conditions, to give alkyl benzenes. So the derivatives that are initially synthesized, they can be converted into other aromatic compounds by subsequent reactions that we are able to do here. Now let's try to explore some synthesis examples based on an understanding of these reactions. Now, for most of these synthesis reactions, the key step is actually identifying the sequence in which we are going to do the reactions. So if we look at the first synthesis here, where benzene is converted into a derivative, and now the derivative has two substituents on it. So there's a bromo group and there is a nitro group on it. So by seeing these two groups, what we can identify is we need to do two reactions here. We have to do a bromination, and second, we have to do a nitration. In fact, I should not say second, we have to do a bromination and we have to do a nitration. And so the big question here is, which sequence should we follow? And by that we mean, should we do the bromination first or should we do the nitration first? And let's see what happens when we do either one of them. So starting from benzene, one possibility is that we do a bromination first. So we react benzene with Br2 in presence of FeBr3. This is going to give us bromobenzene. And now, since we're working with benzene, in principle, I can put that bromine group anywhere on that ring. And once we are done with the bromination, the second step would be to do the nitration, which is done using nitric acid and sulfuric acid. And now recognize that bromine is a halogen which is orthopara directing, which means the nitro group would end up at the ortho position or at the para position. And so this pathway does not give us the product where the bromine and the nitro are meta to each other. So this is one aspect of the product that we have to take note of from the very beginning, actually. So the other possibility is that from benzene, we do a nitration first. So we react benzene with nitric acid and sulfuric acid. This will give us nitrobenzene. Again, you could put the nitro group anywhere on the ring at this point. And now our substituent is a nitro group, which is meta directing. So if we do a bromination on this nitrobenzene molecule using Br2 and FeBr3, it is going to give us the desired product where the bromine and the nitro are meta to each other. So we are able to get the desired products using the sequence. So that means the correct sequence is going to be to do the nitration first and follow that with a bromination to get to the product. So as you can see, what's important here is choosing the sequence of the reactions that we are going to do. So for the second example here, again, we start with benzene. And benzene is converted into this compound which has a chloro group and an amino group on it. Now, we cannot put an amino group directly, but we saw earlier that an amino group can be obtained by reducing a nitro group. Okay, so the reactions that we're going to do here seems like they are a chlorination and we need to do a nitration followed by a reduction. So there are basically three reactions: a chlorination, a nitration, and a reduction. And again, the sequence of these reactions is what's important over here. So one possibility here is that we do a chlorination first. So we'll use chlorine and AlCl3. This would give us the chlorobenzene, or it would give us the chlorine substituted benzene. Now we cannot install an NH2 group directly, so we'll have to do the nitration. So we can try to do a nitration on this molecule. But what we're going to quickly realize is that the chloro group here is orthopara directing. And so it would not give us the required regiochemistry here, which is meta between the chlorine and the amino group. So this synthesis is not going to work out. A second possibility is that we start with benzene and we do the nitration first. This will give us nitrobenzene. And now we have to do a reduction. So let's go ahead and try a reduction on this. So we can do the reduction using zinc and HCl, followed by the reaction with sodium hydroxide, or workup with sodium hydroxide. And this would convert the nitro group into an amino group. And then we can try the chlorination on this molecule, chlorine and AlCl3. But again, what we realize is that this amino group, this is an orthopara directing group, which means this strategy again does not give us the required meta regiochemistry between the two groups. So a third possibility is that we start with benzene and we do the nitration to give the nitrobenzene molecule. And before we do the reduction, we are actually going to do the chlorination. So on the nitrobenzene, we do the chlorination. This would give us a meta-chloronitrobenzene, because the nitro group here is meta directing. So we are able to install the chloro group meta to the nitro group. And then finally, we can do the reduction of the nitro group using zinc and HCl, followed by a basic workup. And by doing so, we are able to make the product, the desired product, where the amino group and the chloro are meta to each other. So again, what we notice is that the sequence of these reactions, or the order in which these reactions are conducted, that is the most important factor here. Let's try another example where we are converting benzene into a tri-substituted molecule. And by looking at the functional groups that are installed, it looks like we need to do a bromination. We need to do a nitration, and we have to do a Friedel-Crafts acylation reaction. So there are three reactions. And something else that's important to keep in mind is the regiochemistry of these groups. So the bromo and the nitro group are ortho to each other, and the nitro and the acyl group are meta to each other. So let's try out the various possibilities here. So let's start with a bromination first. So if we do a bromination on benzene, is going to yield us bromobenzene, where the bromo substituent is ortho-para directing. So let's try the acylation, the Friedel-Crafts acylation. So we're going to use CH3COCl because that's the acyl, the group that we have, and aluminum trichloride, and this would give us a product where we have the bromo and the acyl group at the para position. And at this point we have two groups, the bromo group which is ortho-para directing and the acyl group which is meta directing. And so now if we do a nitration after this as the third reaction, it is going to give us the expected product because the ortho position to the bromine and the meta position to the acyl group are at the same carbon. It is the ortho position of the bromine, which is also the meta position to the acyl group. So both those groups are directing the incoming electrophile, the nitronium ion, to that position. So this synthesis would work actually. So this is a good synthesis that we've done. Let's try switching the sequence of these reactions. So let's think that we started with a nitration instead. So if we did the nitration on benzene first, so that will give us nitrobenzene. And if we do a bromination afterwards, it is going to install the bromine meta to the nitro group. But what we notice is that the bromine is ortho to the nitro group, and what's meta to the nitro group is the acyl group. So seems like a more logical pathway would be to do the acylation afterwards. So we can take the nitrobenzene and do a Friedel-Crafts acylation. So that's going to give us the nitro group and the acyl group on it, which are meta to each other. So that is the regiochemistry that we are seeing in the product. Those two groups are meta to each other. Now, the last reaction that we have to do is the bromination. So Br2 and FeBr3. But at this point, what we notice is that both of the directing groups on this molecule at this point are meta directing. And so they are both going to send the incoming bromine to this meta position. And this does not yield us the product that we want because we want the bromine ortho to the nitro group. Now, if we tried a similar synthesis where we do the acylation first and the nitration later, even that's not going to work here because we will run into a similar issue here. So it looks like in this particular case, the best synthesis is the first synthesis that we came up with. So we do a bromination first to install the bromine group. Then we do a Friedel-Crafts acylation to install the acyl group, para to the bromine molecule here, and then finally a nitration to install the nitro group, which is meta to the acyl group and ortho to the bromine group. I hope you find these examples helpful. Bye.